So here's something worth thinking about as you settle in tonight. Everything around you right now, the pillow under your head, the blanket over your shoulders, the air you're breathing, the phone or speaker playing this, all of it, every single bit of it, is made of the same tiny handful of ingredients. And I mean tiny. Not tiny like grains of sand. Tiny like, well, tiny like nothing you've ever seen or could ever see, because these things are so small that the word small doesn't really do the job anymore. We're talking about particles, the fundamental bits of stuff that make up everything. And I mean everything. You, me, the moon, the ocean, a cup of coffee, a star 800 light years away. Same ingredients. Same recipe book. Just different pages. And here's what's kind of wonderful about that. For most of human history, people have suspected this was the case. Long before anyone had a particle accelerator or a cloud chamber or even a decent microscope, people looked at the world and thought, you know what? There's probably some basic set of building blocks underneath all of this. Some simple foundation holding the whole show together. That intuition, that the universe is at bottom simpler than it looks. That's one of the oldest ideas in science. Maybe one of the oldest ideas, period. Let's start there. Let's start way back, because the story of particle physics doesn't begin in a laboratory. It begins with a question, and the question is one you've probably asked yourself in some form. What is stuff made of? Around 2,400 years ago, give or take, a Greek philosopher named Democritus was wrestling with exactly this. Democritus lived in the city of Abdera in northern Greece around 400 BC, and he had this thought experiment. Imagine you take a piece of cheese, or bread, or stone, or whatever you like, and you cut it in half. Then you take one of those halves and cut it in half again, and again, and again. How far can you go? Can you keep cutting forever, getting smaller and smaller and smaller pieces? Or do you eventually hit some limit? Some point where you've got the smallest possible piece, something that can't be divided any further? Democritus said yes, there's a limit. You'd eventually reach a piece so small and so fundamental that it couldn't be cut anymore. And he called these pieces atomos, which literally means uncuttable in Greek. Atoms, the uncuttable things. Now, Democritus didn't have any way to prove this. He didn't run experiments. He was reasoning purely from logic and intuition, which is a beautiful and also deeply unreliable way to do science. But his intuition was remarkable. He imagined that everything in the world was made of these tiny, indivisible particles moving through empty space, bumping into each other, clumping together in different arrangements to make different substances. Water was made of smooth, round atoms that could slide over each other. Iron was made of atoms with hooks that locked together. It's a gorgeous picture. And while the details are wrong, atoms don't have hooks, water atoms aren't round, the core idea is shockingly close to what we believe today. That matter is made of discrete particles, that the variety we see in the world comes from different combinations and arrangements of a smaller set of fundamental pieces. But here's the thing. Democritus lost the argument, at least for a while. A very long while. His contemporary Aristotle, who was, let's be honest, probably the most influential thinker in Western history, disagreed completely. Aristotle said matter was continuous. You could keep dividing forever. There were no atoms. Instead, everything was made of 4 elements: earth, water, air, and fire, mixed in different proportions. And because Aristotle's word carried so much weight, And because his system was elegant and seemed to explain a lot of everyday experience, the idea of atoms was essentially shelved for about 2,000 years. 2,000 years. Think about that. One of the most important ideas in the history of science, just sitting on a shelf, gathering dust, because the wrong guy won the debate. And that's worth pausing on for a second, because it tells you something about how science actually works. It's not a straight line from ignorance to knowledge. It's messy. It backtracks. Good ideas get buried. Bad ideas flourish. Sometimes the truth has to wait a very, very long time for someone to come along and dig it back up. So let's jump forward, way forward, to the 1800s. Because that's when atoms finally start to come back into the conversation, and this time, there's actual evidence. The person who really gets the ball rolling is an English school teacher and chemist named John Dalton. Dalton was born in 1766 in a small village in the Lake District, Eaglesfield, population not very many. He was a Quaker, largely self-taught, and he had this quiet, methodical personality that turned out to be exactly what the question needed. In the early 1800s, Dalton was studying how gases behaved, how they mixed, how they combined in chemical reactions, and he noticed something. When elements combined to form compounds, they always did so in fixed, simple ratios by weight. Water was always 8 parts oxygen to 1 part hydrogen by mass. Carbon dioxide was always a specific ratio of carbon to oxygen. Always. Not approximately, not roughly. Always exactly the same ratio. And Dalton realized that the simplest explanation for this was atoms. If elements were made of tiny, identical particles, atoms, each with a specific weight, then of course they'd combine in fixed ratios. 1 atom of this hooks up with 1 atom of that, or 2 atoms of this with 1 atom of that, and you get a compound. The ratios are fixed because the atoms are discrete. You can't have half an atom of oxygen. It's 1 or 2 or 3, whole numbers, and that's why the proportions are always clean. Dalton published his atomic theory in 1808, and it was a landmark. Not because it was perfect. He got some things wrong, including the relative weights of several atoms, but because it took the ancient Greek intuition and put it on a foundation of actual experimental evidence. Atoms weren't just a philosophical idea anymore. They were a scientific hypothesis that made specific, testable predictions. But even then, not everyone was convinced. And this is something that might surprise you. The debate over whether atoms were real, like physically real, not just a useful mathematical fiction. That debate wasn't fully settled until the early 1900s. There were serious, respected scientists in the late 1800s who thought atoms were just a convenient way to do calculations, a bookkeeping trick, not actual things. The Austrian physicist Ernst Mach, for instance, was deeply skeptical. He reportedly asked, "Have you seen one?" Which, fair enough, nobody had. The person who did the most to settle this was, of all people, Albert Einstein, and not with relativity. In 1905, the same miraculous year he published his papers on special relativity and the photoelectric effect, Einstein also published a paper on Brownian motion. Brownian motion is this phenomenon where tiny particles, like pollen grains, suspended in water, jiggle around randomly when you look at them under a microscope. It had been observed since the 1820s, when the botanist Robert Brown first noticed it, but nobody had a satisfying explanation. Einstein showed, mathematically, that the jiggling was caused by the pollen grains being bombarded by water molecules, by atoms, too small to see individually, but collectively strong enough to push the pollen around. And he made specific predictions about how much the pollen should move, predictions that depended on the size and number of atoms in the water. A few years later, the French physicist Jean Perrin did the experiments, measured the motion, and confirmed Einstein's predictions almost exactly. That was it. After that, the atomic skeptics didn't have much ground left to stand on. Atoms were real. They were actual, physical things, not just a useful idea. And by the early 20th century, scientists were starting to ask the next obvious question. Okay, so atoms are real, but what are they? What's inside them? Are they truly indivisible, like Democritus imagined? Or is there something deeper? And this is where the story gets really good. Because it turns out atoms are not indivisible at all. They're not even close to being the smallest things. They're more like, think of them like tiny solar systems. Or actually, don't think of them like tiny solar systems. That analogy is going to cause us trouble later. But for now, just know that atoms have internal structure. They're made of smaller pieces, and discovering those pieces, figuring out how they fit together, understanding the rules they follow, that's the story of particle physics. That's what we're going to be exploring tonight. The first hint that atoms had parts came from a beautifully simple experiment. In the 1890s, a British physicist named J.J. Thomson was studying something called cathode rays. Here's the setup. You take a glass tube, pump almost all the air out of it, so you've got a near vacuum inside, seal metal plates called electrodes into each end, and then run a high voltage across them. When you do this, something streams from the negative electrode, the cathode, toward the positive electrode. A ray, a glow. Something is clearly traveling through that tube. The question was, what is it? Some scientists thought cathode rays were a type of light, electromagnetic waves, like the ones Heinrich Hertz had recently demonstrated. Others thought they were streams of particles. Thomson devised a series of clever experiments to find out. He showed that cathode rays could be deflected by electric fields and by magnets, which light cannot be. That meant they were charged particles. Then, by measuring how much they were deflected, he could figure out the ratio of their electric charge to their mass. And here's what stunned him. These particles were incredibly light, absurdly light, about 1,800 times lighter than the lightest known atom, hydrogen. Thomson announced his results in 1897, and the implication was enormous. These particles, which he initially called corpuscles, and which we now call electrons, were smaller than atoms. They came from inside atoms, which meant atoms were not, in fact, the uncuttable bedrock of reality. There was a deeper layer. Now, Thomson was a fascinating character. He ran the Cavendish Laboratory at Cambridge, which was arguably the most important physics lab in the world at the time, and he had this gift for attracting brilliant students. 7 of his research assistants went on to win Nobel Prizes. 7. He won one himself in 1906 for discovering the electron. And here's a lovely bit of irony that we'll come back to later. His son, George Paget Thomson, also won a Nobel Prize for proving that electrons behave like waves. The father proved they were particles. The son proved they were waves. Both were right, and figuring out how both can be right at the same time is one of the deepest puzzles in all of physics. But we'll get to that. For now, let's stay with Thomson and his electrons, because he had a problem. He'd found these tiny, negatively charged particles inside atoms. But atoms, as a whole, are electrically neutral. They have no net charge. So if there are negative charges inside, there must be positive charges too, balancing things out. But where? What did the positive part look like? Thomson proposed a model. He imagined the atom as a sphere of positive charge, spread out evenly, with the tiny electrons embedded in it like raisins in a pudding. This became known as the plum pudding model, plum pudding being a traditional British dessert where raisins are scattered through a cake-like matrix. It's a charming image. The atom as a little dessert. And it seemed reasonable. The positive charge was diffuse, spread throughout the atom, and the electrons sat inside it, held in place by electrical attraction. It was wrong. Spectacularly, beautifully wrong. And the person who proved it wrong was one of Thomson's own former students, a brash New Zealander named Ernest Rutherford, who had come to Cambridge on a scholarship and would go on to become one of the most important experimental physicists who ever lived. Rutherford was the kind of scientist who believed that if you couldn't explain your results to a barmaid, you probably didn't understand them yourself. He was loud, confident, and had an almost supernatural instinct for designing experiments that cut right to the heart of a question. In 1909, Rutherford was working at the University of Manchester, and he suggested an experiment to two of his colleagues, Hans Geiger and Ernest Marsden. Marsden was an undergraduate at the time, barely 20 years old. The experiment was conceptually simple. They would take a thin sheet of gold foil, incredibly thin, just a few hundred atoms thick, and fire tiny, fast-moving, positively charged particles at it. These particles were alpha particles, which Rutherford had already identified as being emitted by radioactive elements. They were basically helium atoms, stripped of their electrons, little nuggets of positive charge moving at tremendous speed. The idea was to see what happened when these alpha particles hit the gold foil. If Thomson's plum pudding model was right, and the positive charge in gold atoms was spread out evenly like a diffuse cloud, then the alpha particles should punch straight through with barely any deflection. Maybe a slight wobble, like a bullet going through fog. And most of them did exactly that. Most alpha particles went straight through the foil as if it were barely there. But some of them, a small fraction, bounced back, not just deflected sideways, bounced back, came flying back toward the source. Rutherford later said it was as if you'd fired an artillery shell at a piece of tissue paper and it came back and hit you. It was, he said, the most incredible event of his life. And what it meant was that the positive charge in the atom wasn't spread out at all. It was concentrated in a tiny, dense core, what Rutherford called the nucleus. Almost all the mass of the atom and all of its positive charge was packed into this minuscule central point, and the electrons orbited far away, relatively speaking. The atom was mostly empty space. Vast, astonishing empty space. If the nucleus were the size of a marble sitting at the center of a football stadium, the electrons would be tiny gnats buzzing around somewhere up in the nosebleed seats. Everything in between. Nothing. Just emptiness. That's a staggering thing to sit with. The chair you're lying on, your own body, the floor beneath you. It's almost entirely empty space. The reason it feels solid, the reason you don't fall through the floor, has to do with electromagnetic forces between electrons, not with matter being packed tightly together. At the atomic level, matter is gossamer. It's barely there. And yet here we are, feeling very solid indeed. Rutherford published his nuclear model of the atom in 1911, and it changed everything. But it also created a new problem, a serious one, and it's a problem that would eventually crack open the door to an entirely new way of understanding the universe. Because according to the physics that everyone knew and trusted at the time, classical physics, the physics of Newton and Maxwell, Rutherford's atom was impossible. It couldn't exist. An electron orbiting a nucleus is a charged particle moving in a circle, and classical electromagnetism says that a charged particle moving in a circle must radiate energy. It must give off light. And as it radiates energy, it loses speed, spirals inward, and crashes into the nucleus. The math was unambiguous. Every atom in the universe should collapse in about 100 millionth of a second. Obviously, atoms don't collapse. You're made of atoms that have been perfectly stable for billions of years. So something was deeply, fundamentally wrong with the classical picture. And the person who took the first real crack at fixing it was a quiet, thoughtful Danish physicist named Niels Bohr, who arrived at Rutherford's lab in Manchester in 1912 and started thinking very carefully about what was really going on inside an atom. Bohr was only 26 years old, and he'd come to Manchester to work with Rutherford on radioactivity. But the problem of the impossible atom kept pulling at him. He couldn't let it go. And here's what's interesting about Bohr. He wasn't the flashiest physicist of his generation. He wasn't a mathematical prodigy like some of the people we'll meet later. He was slow and deliberate. He'd write a sentence, cross it out, rewrite it, cross it out again, dictate to his wife or a colleague, pace around the room, mumble to himself. His papers went through draft after draft after draft. But he had something that turned out to be more valuable than raw mathematical speed. He had an extraordinary physical intuition, a willingness to say, I don't care if this breaks the old rules, because the old rules are clearly wrong here. So let me just follow what the experiments are telling me and see where it leads. And what the experiments were telling him was strange. See, there was another puzzle floating around at the time, something that seemed unrelated to the structure of the atom, but turned out to be deeply connected. When you heat a gas, hydrogen say, and look at the light it gives off through a prism, you don't see a smooth rainbow of colors. You see specific, sharp lines, very particular wavelengths of light, with darkness in between. Hydrogen always gives off the same lines, always the same colors, the same wavelengths, down to many decimal places. People had known about these spectral lines since the 1850s, and a Swiss schoolteacher named Johann Balmer had even found a neat mathematical formula in 1885 that predicted the wavelengths of hydrogen's visible lines. But nobody knew why. Why those particular wavelengths? Why not a smooth spectrum? It was just a pattern without an explanation, like finding a sequence of numbers scratched into a wall with no context. Bohr looked at this, and he looked at Rutherford's atom, and he had one of those moments, one of those quiet, world-changing moments, where two seemingly separate puzzles click together. What if, he thought, electrons can't just orbit the nucleus at any distance they like? What if there are only certain allowed orbits, specific distances, specific energies, and nothing in between? If that were true, then an electron sitting in one of these allowed orbits wouldn't radiate energy, because it just wouldn't. Bohr essentially declared it by fiat. He said, look, I know classical physics says it should radiate, but it doesn't, so there must be a new rule. In these special orbits, the electron is stable. Period. And then, here's the beautiful part. When an electron jumps from a higher orbit to a lower one, it releases energy in the form of light. And the amount of energy it releases corresponds to the difference between those two orbits. That energy comes out as a photon with a very specific wavelength, a very specific color. Think about what that means. If there are only certain allowed orbits, then there are only certain allowed jumps between orbits, which means there are only certain allowed wavelengths of light that the atom can emit. Specific lines. Exactly what people had been seeing through their prisms for 60 years. Bohr published this model in 1913, and when he plugged in the numbers, using Planck's constant, the charge of the electron, the mass of the electron, his formula spit out exactly the wavelengths that Balmer had found empirically. Exactly. Not approximately, not close enough. Exactly. That's a spine-tingling moment in the history of science. A theoretical model built on a strange new assumption that nobody fully understood, predicting experimental results to extraordinary precision. Rutherford himself was impressed, but a little uneasy. He wrote to Bohr asking how the electron decides which orbit to jump to. It was a fair question, and Bohr didn't really have a good answer. Nobody did, not yet. Now, I should mention something that was already in the air before Bohr, because his model didn't come out of nowhere. It built on an idea that had been introduced 13 years earlier by a German physicist named Max Planck. And Planck's story is worth lingering on for a moment, because it's one of those cases where a person makes a revolutionary discovery almost against their own will. It was the year 1900, and Planck was working on a problem called black body radiation, basically the question of how a hot object emits light. If you heat a piece of metal, it glows, first red, then orange, then white. The question was, can you predict exactly how much light it emits at each wavelength for a given temperature? Classical physics had two different formulas, and each one worked for part of the spectrum, but failed catastrophically for the rest. One of them, the Rayleigh-Jeans formula, actually predicted that a hot object should emit infinite energy at short wavelengths, which was obviously absurd. This was called the ultraviolet catastrophe, which is honestly one of the best names for a physics problem ever. Planck was a conservative, meticulous physicist. He wasn't looking to overthrow anything. He just wanted to find the right formula. And he did find it. By trial and error almost, he constructed a mathematical expression that fit the experimental data perfectly across all wavelengths. But when he tried to derive that formula from first principles, the only way he could make it work was to assume that energy wasn't emitted continuously, in smooth flows, but in tiny discrete packets. Little chunks. He called them quanta, from the Latin word for how much. Each quantum of energy was proportional to the frequency of the light, with the proportionality constant being a new fundamental number. Planck's constant, h, a number so small it's almost absurd. 6.626 times 10 to the negative 34 joule seconds. Tiny, but not zero. And that made all the difference. Planck himself didn't fully appreciate what he'd done. He thought the quantization was maybe just a mathematical trick, an accounting device that happened to give the right answer. He spent years trying to find a way to get the same result without it. He couldn't. And meanwhile, other people started picking up the idea and running with it. Einstein, in 1905, the same miraculous year he explained Brownian motion, used Planck's quantum idea to explain the photoelectric effect, the observation that light shining on a metal surface can knock electrons loose, but only if the light's frequency is high enough. Brighter light of too low a frequency does nothing, which makes no sense if light is a smooth wave. Einstein proposed that light itself comes in quanta. Particles of light, which we now call photons. Each photon carries an energy proportional to its frequency. If a single photon doesn't carry enough energy to knock an electron free, then it doesn't matter how many of them you throw at the metal. None of them can do the job individually, so the electron stays put. This was radical. Light as particles? People had spent a century proving that light was a wave. Thomas Young's double-slit experiment back in 1801 had shown interference patterns, light behaving exactly like ripples in a pond. Maxwell's equations described light as electromagnetic waves. And now Einstein was saying, actually, it's also particles? Both at once? The physics community was not thrilled. Even Planck, who'd started the whole quantum business, thought Einstein had gone too far. But here's the thing. It worked. It explained the photoelectric effect perfectly, and it would eventually earn Einstein his Nobel Prize in 1921. Not relativity, not E equals mc squared. The photoelectric effect. That's what the Nobel Committee cited, which tells you something about how important this quantum idea was becoming. So when Bohr built his atomic model in 1913, he was standing on this foundation. Planck had introduced quantization of energy. Einstein had extended it to light itself. And now Bohr was applying it to the structure of the atom, saying that the electron's energy inside an atom is quantized, that it can only take certain specific values, and that transitions between these values produce the spectral lines that everyone had been puzzling over. 3 steps, 3 different physicists, over 13 years, each one building on the last, each one a little more radical than the one before. Bohr's model was a triumph, but it was also, honestly, a bit of a mess. It worked beautifully for hydrogen. 1 proton, 1 electron, the simplest atom there is. But when people tried to extend it to helium, with 2 electrons, it started to break down. The predictions didn't match the experiments nearly as well. And the model had this uncomfortable ad hoc quality to it. Why were only certain orbits allowed? Bohr had postulated it, but he hadn't really explained it. It felt like a rule imposed from outside rather than something that emerged naturally from deeper principles. It was like finding that a clock keeps perfect time, but not understanding the mechanism inside. You know it works, but you don't know why it works. And that's unsatisfying if you're a physicist. What was needed was a deeper theory, a more complete framework that would explain Bohr's quantization rules as natural consequences of something more fundamental, and that would work for all atoms, not just hydrogen. And that deeper theory was coming. It was brewing in the minds of a remarkable generation of young physicists scattered across Europe, in Göttingen, in Copenhagen, in Cambridge, in Munich, in Vienna. The decade from about 1923 to 1933 would become one of the most extraordinary periods of intellectual achievement in human history. In just 10 years, a handful of people, most of them in their 20s, would completely reinvent our understanding of reality at its most fundamental level. And the first major breakthrough came from a young French aristocrat with an unusual background for a physicist. His name was Louis de Broglie, and before he turned to physics, he'd studied medieval history. His older brother Maurice was an experimental physicist who worked with X-rays, and something about the family dinner conversations must have sparked Louis's curiosity, because he switched fields and started thinking about a question that seems almost naive when you first hear it, but turned out to be one of the most profound questions in all of physics. If light, which everyone had agreed was a wave, could also behave like a particle, like Einstein had shown with the photoelectric effect, then could things that everyone agreed were particles, like electrons, also behave like waves? Just sit with that for a moment. It's such a simple inversion. Einstein had taken something wavy and shown it had a particle side. De Broglie was asking whether things with a particle side might also have a wavy side. It's the kind of symmetry argument that feels almost too elegant, almost too neat. But de Broglie didn't just ask the question. he worked out the math. In his 1924 doctoral thesis, his doctoral thesis, mind you, not some magnum opus written over decades, he proposed that every particle has an associated wavelength, and he gave a formula for it. The wavelength equals Planck's constant divided by the particle's momentum. That's it. Lambda equals h over p. Planck's constant, that tiny number we talked about earlier, divided by mass times velocity. Now here's what's clever about this formula and why it explains something important about everyday life. Planck's constant is incredibly small. It's on the order of 6.6 times 10 to the negative 34. So if you take any object with everyday mass and everyday speed, say a baseball flying through the air, and you plug those numbers in, the wavelength you get is absurdly, incomprehensibly tiny. Way smaller than an atom, way smaller than a nucleus, way smaller than anything you could ever hope to detect. Which means that for baseballs and cars and people and planets, the wave nature is there in principle, but it's so vanishingly small that it's completely undetectable. It has no practical effect whatsoever. That's why we never notice it. That's why classical physics works perfectly well for the everyday world. But for an electron has a mass of about 9 times 10 to the negative 31 kilograms. That's extraordinarily light. And when you plug that into de Broglie's formula with the kind of speeds electrons typically move at inside atoms, you get a wavelength that's roughly the size of an atom itself, on the order of angstroms, tenths of a nanometer. And that changes everything. Because now the wave nature isn't negligible anymore. It's comparable to the scale of the system the electron is moving in. The electron's wavelength is about the same size as the atom it's orbiting, and that means you can't ignore the wave behavior. It dominates. And here's the beautiful part. Here's why de Broglie's idea immediately made Bohr's model make sense in a deeper way. Remember how Bohr had just postulated that only certain orbits were allowed? Certain specific radii where the electron could exist, and nothing in between? De Broglie's picture gives you a reason for that. Think of it this way. Imagine the electron as a wave wrapping around the nucleus in a circular orbit. For that wave to be stable, for it to sustain itself, it has to come back around and meet itself in phase. It has to form what's called a standing wave. If it doesn't, the wave interferes destructively with itself and cancels out. It's like a vibrating guitar string. A guitar string can only vibrate at certain frequencies, the fundamental and the harmonics, because the wave has to fit neatly between the two fixed ends. Any wavelength that doesn't fit just dies out. Same idea here, but wrapped in a circle instead of stretched in a line. The circumference of the orbit has to equal a whole number of wavelengths. 1 wavelength, 2 wavelengths, 3, 4, but not 1.5, not 2.7. A whole number. And when you write that condition down mathematically and combine it with de Broglie's formula, you get exactly Bohr's quantization rule. Exactly. The allowed orbits fall right out naturally. They're not imposed from outside anymore. They emerge from the wave nature of the electron. De Broglie presented this in his thesis at the University of Paris in 1924. The story goes that his thesis committee wasn't entirely sure what to make of it. It was bold, it was speculative, and it was based on an analogy rather than rigorous derivation. They apparently sent a copy to Einstein to ask his opinion, and Einstein replied that he thought de Broglie had lifted a corner of a great veil. That's high praise from Einstein. De Broglie got his doctorate, and he would eventually win the Nobel Prize in 1929 for this work. But the real test was whether anyone could actually detect these matter waves. If electrons really behaved like waves, you should be able to see wave-like phenomena, interference, diffraction, when you shoot electrons at things. And in 1927, that's exactly what happened. Clinton Davison and Lester Germer, working at Bell Labs in the United States, fired electrons at a nickel crystal and observed a diffraction pattern. The electrons were bouncing off the regularly spaced atoms in the crystal lattice and interfering with each other, just like X-rays do, just like any wave does when it encounters a periodic structure. The pattern matched de Broglie's predicted wavelength perfectly. Independently, George Paget Thomson, and yes, he was J.J. Thomson's son, which is one of those wonderful historical rhymes, did similar experiments in Scotland, firing electrons through thin metal foils and seeing diffraction rings. The father discovered the electron as a particle. The son helped prove it was also a wave. Both won Nobel Prizes. You can't make this stuff up. So by the mid-1920s, the situation was genuinely strange. Light was both a wave and a particle. Electrons were both a particle and a wave. This duality wasn't a confusion or a contradiction to be resolved. It was turning out to be a fundamental feature of nature. And the question became, how do you build a proper mathematical theory around this? How do you write equations for something that's somehow both a wave and a particle at the same time? Two answers emerged almost simultaneously, and the story of how they developed is one of the great dramas of 20th century science. The first came from a young German physicist named Werner Heisenberg, and the way he arrived at it is remarkable. In the summer of 1925, Heisenberg was 23 years old. He'd been working in Göttingen with Max Born and had spent time in Copenhagen with Bohr. He was brilliant, ambitious, and deeply frustrated with the state of atomic physics. All these models with their orbits and trajectories, he felt they were fundamentally misguided because you could never actually observe an electron orbiting. You could only observe the light that atoms emitted and absorbed, the spectral lines, the frequencies and intensities. So Heisenberg decided to build a theory based only on observable quantities. Forget about orbits, forget about trajectories. Just work with the numbers you can actually measure. He went to the island of Helgoland in the North Sea to recover from a bad bout of hay fever. His face was so swollen he could barely see. And there, working alone, mostly at night because his allergies were worse during the day, he developed a new mathematical framework. Instead of describing an electron's position and velocity, he arranged the observable quantities, transition frequencies, and amplitudes between energy states into arrays of numbers, tables of numbers, organized in rows and columns that you could multiply together according to specific rules. When he multiplied two of these arrays together, he noticed something strange. The order of multiplication mattered. A times b did not equal b times a. That's not how regular numbers work. 5 times 3 is the same as 3 times 5. But Heisenberg's arrays didn't commute, as mathematicians say. He found this disturbing. He later recalled being so unsettled that he couldn't sleep, and went for a walk on the rocky shore of Helgoland in the middle of the night, climbing a cliff to watch the sunrise. But when he brought his work back to Göttingen and showed it to Max Born, Born immediately recognized what Heisenberg had reinvented. These arrays of numbers with their non-commutative multiplication, they were matrices, a well-established branch of mathematics that physicists at the time rarely used. Born, along with his student Pascual Jordan, helped Heisenberg formalize the theory into what became known as matrix mechanics. It was published in a series of papers in 1925 and early 1926, and it worked. It gave the right answers for the hydrogen atom, for spectral line intensities, for everything they threw at it. But here's the thing. Almost nobody could understand it. Matrix mechanics was abstract, unfamiliar, and deeply counterintuitive. Most physicists in the 1920s had never worked with matrices. The theory seemed to have abandoned any attempt to visualize what was happening inside the atom. It just gave you rules for calculating observable quantities, and those rules involved this strange, non-commutative algebra. It was powerful, but it felt alien. And then, just a few months later, a completely different approach appeared, and it came from a very different kind of physicist. His name was Erwin Schrödinger, and he was Austrian, older than most of the quantum revolutionaries, 38 when he did his most famous work, which in that crowd of 20-somethings practically made him elderly. Schrödinger was a man of wide interests and complicated personal life, a lover of philosophy and poetry, someone who found Heisenberg's matrix mechanics ugly and repellent. He wanted something he could visualize. He wanted waves. Taking de Broglie's idea of matter waves as his starting point, Schrödinger set out to find a wave equation for the electron, a differential equation, the kind physicists were comfortable with, the kind that described how a wave evolves in space and time. And over Christmas of 1925, during a holiday in the Swiss Alps, at a villa in Arosa, accompanied by a woman who was not his wife, a detail that biographers have noted with varying degrees of discretion, he found it. The equation that would bear his name, the Schrödinger equation. He published it in early 1926 in a series of 4 papers that landed like a thunderbolt. Where Heisenberg's matrix mechanics was abstract and algebraic, Schrödinger's wave mechanics was visual and familiar. It described a wave function, usually written with the Greek letter psi, that spread through space and evolved smoothly in time according to a beautiful partial differential equation. Physicists loved it. They could picture it. They could work with it. They could solve it for the hydrogen atom and get all the right energy levels, the same ones Bohr had found, the same ones Heisenberg's matrices gave, but now emerging from a smooth, continuous wave equation. There was just one deeply puzzling question that Schrödinger himself struggled with, and it's a question that in some sense we're still grappling with today. What exactly is the wave function? What is this psi thing that's waving? When you have a water wave, it's the surface of the water moving up and down. When you have a sound wave, it's pressure variations in the air. When you have a light wave, it's oscillating electric and magnetic fields. But the electron's wave function, what medium is it a wave in? What physical quantity is oscillating? Schrödinger initially thought it might represent the electron's charge smeared out through space, like a cloud of electricity. But that interpretation ran into problems almost immediately, and the person who figured out what the wave function actually means was Max Born, a German physicist working at Göttingen, a man who'd already helped Heisenberg formalize matrix mechanics and who had a deep, almost philosophical instinct for what physics could and couldn't tell you about the world. Born looked at Schrödinger's wave function and proposed something radical, something that Schrödinger himself never fully accepted. Born said the wave function doesn't represent the electron itself smeared out through space. It represents the probability of finding the electron at a given location. More precisely, if you take the wave function psi at some point in space and you calculate its square, technically the square of its absolute value, since psi can be a complex number, what you get is the probability density. The likelihood, per unit volume, that if you go looking for the electron right there, right at that spot, that's where you'll find it. Think about what that means. The wave function isn't a physical wave in any ordinary sense. It's not a thing sloshing around. It's more like a map of possibilities. Where psi squared is large, the electron is likely to be found. Where psi squared is small, it probably won't be. And where psi is 0, the electron will never show up there at all. Bohr published this interpretation in 1926, the same year Schrödinger's papers appeared, and it was one of those ideas that sounds simple when you state it, but absolutely transforms everything when you follow through on its implications. Because if the wave function is fundamentally about probabilities, then quantum mechanics is telling you something shocking about the nature of reality. It's telling you that at the most fundamental level, the universe doesn't determine exactly what will happen. It only determines the odds. This was not a popular idea with everyone. Einstein hated it. He famously wrote to Bohr, and they were friends, by the way. They corresponded for decades. He wrote that he was convinced God does not play dice. That line gets quoted all the time, and it's worth sitting with for a moment, because Einstein wasn't being flippant. He genuinely believed that the probabilistic nature of quantum mechanics was a sign that the theory was incomplete, that there must be some deeper layer of reality, some hidden variables beneath the quantum description that would restore determinism if only we could find them. Schrödinger wasn't thrilled either. He'd created this beautiful wave equation, hoping it described something real, something physical, a genuine wave in space. And now Bohr was saying no, it's just a probability tool. Schrödinger once remarked that if he'd known what his equation would be used for, he never would have invented it, which is a pretty extraordinary thing for a physicist to say about his own greatest achievement. But Bohr's interpretation worked. It was consistent. It made correct predictions. And it connected beautifully with Heisenberg's uncertainty principle, which Heisenberg formulated in 1927. Here's where things get really interesting. So let's slow down and talk about this carefully. Heisenberg's uncertainty principle is one of the most misunderstood ideas in all of physics. People sometimes describe it as saying that you disturb a particle when you measure it, like you're clumsy, and you bump the electron when you try to look at it. And there's a grain of truth in that picture. Heisenberg himself used a thought experiment involving a gamma-ray microscope that kind of suggested that interpretation. But the deeper truth is more profound and more strange. The uncertainty principle says that certain pairs of physical properties are fundamentally linked in a way that prevents you from knowing both of them precisely at the same time. Position and momentum are the classic pair. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. And this isn't because your instruments aren't good enough. It's not a limitation of technology. It's a feature of reality itself. The particle doesn't have a precise position and a precise momentum simultaneously. Those properties simply aren't both defined at the same time. The mathematical statement is elegant. The uncertainty in position multiplied by the uncertainty in momentum is always at least as large as Planck's constant divided by 4 pi. And there's that constant again, Planck's h, showing up like a signature, marking the boundary between the classical world where things have definite properties and the quantum world where they don't. For anything large, like a baseball or a person, the uncertainties required by this principle are so absurdly tiny that they're unmeasurable. You'd never notice. But for an electron, the constraints are enormous relative to the scales that matter. Now, here's what's beautiful about how all of this connects. Remember de Broglie's idea that particles have wavelengths? And remember how Schrödinger turned that into a wave equation? Bohr's probability interpretation and Heisenberg's uncertainty principle aren't separate add-ons to the theory. They're natural consequences of the wave nature of matter. If you've ever played with waves, water waves, sound waves, anything, you know that a wave that's spread out over a large region has a well-defined wavelength, but no definite position. And a wave that's concentrated in a tiny spike has a definite position, but no single wavelength. You can't have both. That's just the mathematics of waves. So the uncertainty principle falls right out of the wave description. It's not mysterious extra physics, it's what waves do. By 1927, all of these threads, Schrödinger's equation, Born's probability interpretation, Heisenberg's uncertainty principle, and the whole mathematical framework were being woven together into a coherent picture. And the place where that weaving happened, at least symbolically, was the Fifth Solvay Conference in Brussels in October 1927. This is one of those legendary gatherings that physics nerds love to talk about, and for good reason. The photograph from that conference is maybe the most famous group photo in the history of science. 29 physicists, 17 of whom either had or would win Nobel Prizes. Einstein is there, front and center. So is Bohr, and Heisenberg, and Schrödinger, and Born, and Dirac, and Pauli, and Lorentz, and Marie Curie, and Planck. Just an absurd concentration of genius in one room. And what happened at that conference was essentially a showdown. On one side, you had Bohr and Heisenberg and Born and most of the younger generation advocating for what became known as the Copenhagen interpretation. The idea that the wave function is a complete description of a quantum system, that probabilities are fundamental, that you can't peek behind the curtain to find a deterministic reality underneath. On the other side, you had Einstein, deeply uncomfortable with all of this, proposing one clever thought experiment after another, trying to show that quantum mechanics was inconsistent or incomplete. And Bohr, every single time, found the flaw in Einstein's argument. Every time Einstein thought he'd caught quantum mechanics in a contradiction, Bohr showed that the theory held up. It was like watching a chess match between two grandmasters, except the stakes were the nature of reality itself. The debates between Bohr and Einstein continued for years, well beyond that 1927 conference. At the 1930 Solvay conference, Einstein proposed a particularly ingenious thought experiment involving a box of photons and a clock, designed to violate the energy-time uncertainty relation. And Bohr, after a sleepless night of frantic work, realized that Einstein had forgotten to account for his own general theory of relativity, that the gravitational redshift from moving the box in a gravitational field introduced exactly the uncertainty Einstein was trying to eliminate. Einstein had been defeated by his own theory. It's one of the great ironic moments in physics history. But here's the thing, and this matters. Einstein was never really proven wrong in the deepest sense. He was wrong that quantum mechanics was inconsistent. Bohr showed that convincingly. But Einstein's deeper concern, that quantum mechanics might not be the final word, that there might be a more complete theory underneath, that question is genuinely still open. The interpretation of quantum mechanics remains one of the most debated topics in the foundations of physics. The Copenhagen interpretation is the most widely taught, but there are serious alternatives: many worlds, pilot wave theory, objective collapse models, and smart people disagree passionately about which one is right. So Einstein's instinct that something was missing may yet turn out to be vindicated, even if his specific objections were answered. But let's come back to the late 1920s, because while the philosophers were arguing about what quantum mechanics meant, the physicists were busy using it to do extraordinary things. And one of the most extraordinary was the work of Paul Dirac, Dirac was British, born in Bristol in 1902, and he was one of the strangest and most brilliant people in the history of physics. He was almost pathologically quiet. Colleagues joked that a Dirac should be the unit of 1 word per hour. He took everything literally. When someone once said to him at dinner, "It's windy outside," Dirac reportedly got up, went to the door, looked outside, came back, sat down, and said, "Yes." Whether or not that specific anecdote is true, and several versions circulate, everyone who knew him agreed that he was spectacularly, almost comically, laconic. But when he did speak, or more importantly, when he wrote equations, the results were devastating in their elegance. In 1928, Dirac set out to solve a problem that had been nagging at the foundations of quantum mechanics. Schrödinger's equation worked beautifully for describing electrons at low speeds, but it wasn't compatible with Einstein's special relativity. And electrons in atoms, especially heavy atoms, can move at a significant fraction of the speed of light. So you needed a quantum equation that respected relativity, that treated space and time on equal footing the way Einstein's theory demanded. Others had tried. There was an equation called the Klein-Gordon equation that was relativistic, but it had problems. It gave negative probabilities, which don't make physical sense. Dirac wanted something better. And what he found, through a combination of mathematical brilliance and sheer aesthetic instinct, was the Dirac equation. It's one of those achievements that other physicists describe with something close to awe. He essentially took the square root of the Klein-Gordon equation, which sounds like a simple thing to say but is mathematically highly non-trivial, because it required introducing a completely new mathematical structure, 4x4 matrices called gamma matrices, and the wave function had to become a 4-component object called a spinor. The equation was beautiful. It automatically predicted that electrons have spin, a quantum property that had been discovered experimentally but had to be added by hand to Schrödinger's equation. Dirac's equation just gave it to you for free, as a natural consequence of combining quantum mechanics with relativity. That alone would have been remarkable. But then came the truly wild part. The Dirac equation had solutions with negative energy, and not in a way you could just ignore or dismiss as mathematical artifacts. The equation seemed to be saying that for every electron with positive energy, there should be a corresponding state with negative energy. Dirac puzzled over this for a while, and then proposed something audacious. He suggested that all the negative energy states are already filled, occupied by an infinite sea of electrons that we can't see because they're everywhere and uniform, like a background. But if you pumped enough energy into this sea, if a high-energy photon, say, knocked one of those negative energy electrons up into a positive energy state, you'd see 2 things appear: a normal electron and a hole in the sea. And that hole would behave like a particle with the same mass as the electron, but with positive charge. Dirac initially tried to identify this hole with the proton, which was the only positively charged particle known at the time. But the masses didn't work. The proton is almost 2,000 times heavier than the electron. Other physicists, notably Robert Oppenheimer, pointed out that the hole had to have the same mass as the electron. So Dirac was predicting a completely new particle, a positively charged electron, an anti-electron, antimatter. And in 1932, Carl Anderson at Caltech found it. Working with a cloud chamber, a device that makes the paths of charged particles visible as trails of tiny droplets, Anderson photographed a particle that curved the wrong way in a magnetic field. Same mass as an electron, opposite charge. He called it the positron. Dirac's equation, a piece of pure mathematics motivated by the desire for elegance and consistency, had predicted the existence of a form of matter that nobody had ever imagined before. That's worth sitting with for a moment. A mathematical equation, written down on paper, told us something about reality that no experiment had yet revealed. The positron wasn't found because someone went looking for a new particle on a hunch. It was found because the math said it had to be there. And when Anderson saw that track curving the wrong way through his cloud chamber, bending in a magnetic field with the grace of an electron but in the opposite direction, the universe quietly confirmed that Dirac had been right. Mathematics wasn't just describing nature. It was, in some deep and almost unsettling way, anticipating it. And here's the thing. Anderson almost missed it. Or rather, he almost didn't get credit for understanding what he'd found. He'd been studying cosmic rays, those high-energy particles that rain down on Earth from space, smashing into the upper atmosphere and producing cascades of secondary particles. His cloud chamber sat inside a strong magnetic field, and he'd placed a lead plate across the middle of the chamber so he could tell which direction particles were traveling based on how much they slowed down after passing through the plate. When he saw the track of this mystery particle, he could tell from the curvature and the energy loss that it had the mass of an electron, but positive charge. He published his result in 1932, and it was confirmed quickly by others, including Patrick Blackett and Giuseppe Occhialini at Cambridge, who actually had better data, but published slightly later. Anderson got the Nobel Prize in 1936 for the discovery. He was only 31 years old. Now, the positron was the first antiparticle, but Dirac's equation implied something much bigger. It implied that antimatter wasn't a quirk specific to the electron. Every particle should have an antiparticle, a mirror version with the same mass but opposite charge. The antiproton, the antimatter counterpart of the proton, wouldn't be found until 1955, when Owen Chamberlain and Emilio Segre produced them using the Bevatron particle accelerator at Berkeley. The antineutron followed in 1956, and today we can make entire antiatoms, antihydrogen, with a positron orbiting an antiproton, and hold them in magnetic traps for minutes at a time. But all of that traces back to Dirac's equation and Anderson's cloud chamber photograph. So by 1932, the picture of the subatomic world had already gotten wonderfully complicated. You've got the electron, the proton, the neutron, which James Chadwick discovered in 1932 as well, and we should talk about that, the photon, and now the positron. 5 particles. But the story was about to get much stranger, and the cast of characters was about to explode. Let's pause on the neutron for a moment, because Chadwick's discovery is one of those stories that shows how science actually works, not as a single flash of insight, but as a slow accumulation of clues that finally click into place. The neutron had been suspected for over a decade. Rutherford himself had speculated as early as 1920 that there might be a neutral particle in the nucleus, something with roughly the mass of a proton but no electric charge. The reason was simple arithmetic. Take helium. Its nucleus has a charge of +2, suggesting 2 protons. But its mass is 4 times that of hydrogen, not 2 times. Something else was in there. Contributing mass, but not charge. For years, physicists had tried to explain this by imagining that nuclei contained extra protons paired with electrons that neutralized their charge. But this created all sorts of problems, especially with quantum mechanics. You couldn't confine an electron to a space as small as a nucleus without violating the uncertainty principle in ways that didn't make sense. Then in 1930 and 1931, Walter Botha and Herbert Becker in Germany and then Irene and Frédéric Joliot-Curie in Paris. Irene being the daughter of Marie Curie, which is a wonderful piece of scientific dynasty. They all noticed something strange. When they bombarded beryllium with alpha particles, an unusually penetrating radiation came out. The Joliot-Curies thought it was high-energy gamma rays, photons, but Chadwick, working at the Cavendish Laboratory in Cambridge, read their results and immediately suspected something else. He repeated the experiments, carefully measuring how this mystery radiation knocked protons out of paraffin wax, and showed that gamma rays simply couldn't transfer that much momentum. The kinematics didn't work. What could knock protons around like that had to be a particle with roughly the same mass as the proton itself, but with no charge. Otherwise, it would have been deflected by electric fields and easy to spot. In February 1932, Chadwick published his results. The neutron was real. He'd won the race, partly because he had the right theoretical framework in mind, Rutherford's old speculation, and partly because he was just a meticulous, careful experimentalist who trusted the numbers over the assumptions. The neutron changed everything about nuclear physics. Suddenly, you had a clean model of the nucleus, protons and neutrons packed together, with the number of protons determining the element and the number of neutrons varying to create isotopes. But it also raised a huge question, one that's so obvious it's almost embarrassing that it took a while to fully articulate. What holds the nucleus together? Think about it. You've got protons in there, all positively charged, crammed into a space about a femtometer across. That's 10 to the minus 15 meters, absurdly small. Electromagnetic repulsion between those protons is enormous at that distance. Absolutely enormous. So why doesn't the nucleus just fly apart? The answer is that there must be another force, a new force, one that's stronger than electromagnetism, at very short ranges but fades away quickly with distance. This is the strong nuclear force, or as we sometimes call it now, the strong interaction. And in 1935, a young Japanese physicist named Hideki Yukawa proposed a theory for how it works. His idea was beautifully simple in concept, even if the details get technical. He reasoned by analogy with electromagnetism. In quantum electrodynamics, the quantum theory of electromagnetic interactions, the force between charged particles is mediated by the exchange of photons. Two electrons repel each other by tossing virtual photons back and forth. Yukawa said, maybe the strong force works the same way, but with a different carrier particle. And here's the clever part. The photon is massless, which is why the electromagnetic force has infinite range. It falls off with distance, sure, but it never truly reaches zero. Yukawa realized that if the carrier of the strong force had mass, the force would have a finite range. The heavier the carrier, the shorter the range. He could estimate the mass of this hypothetical particle from the known size of the nucleus, and he got something around 200 times the mass of the electron. Heavier than an electron, but lighter than a proton. An in-between particle. A meson, from the Greek word for middle. And then, almost on cue, experimentalists found a particle with roughly the right mass in cosmic ray experiments. In 1936, Anderson, the same Carl Anderson who found the positron, and Seth Nettermeyer discovered a particle in cosmic rays that was indeed intermediate in mass between the electron and the proton. Everyone assumed it was Yukawa's meson, but something was wrong. This particle didn't interact strongly with nuclei the way Yukawa's carrier should. It passed right through matter almost without noticing it. The famous physicist I. Rabi reportedly quipped, "Who ordered that? when the particle's properties became clear. It was the wrong meson. Or rather, it wasn't a meson at all in the nuclear physics sense. It was something else entirely, what we now call the muon. It's essentially a heavier version of the electron, about 207 times heavier, with the same charge and the same spin, but no role in the strong force whatsoever. The muon was the first sign that nature had more particles in store than anyone had bargained for, particles that didn't seem to serve any obvious purpose in the structure of atoms. The actual Yukawa particle, the one that mediates the strong force between protons and neutrons, was found in 1947 by Cecil Powell and his team at the University of Bristol, using photographic emulsions exposed to cosmic rays at high altitude. They called it the pion, or pi meson. It came in 3 varieties: positively charged, negatively charged, and neutral. And it behaved exactly the way Yukawa had predicted. It interacted strongly with nuclei, it had roughly the right mass, and it decayed quickly, as expected for a particle mediating a short-range force. Yukawa received the Nobel Prize in 1949, the first Japanese physicist to be so honored. But now you've got this muon sitting there, unexplained. A particle that looks like a fat electron and doesn't seem to do anything useful. And the muon was just the beginning. Through the late 1940s and into the 1950s, as physicists built bigger and better particle accelerators and continued studying cosmic rays with increasingly sophisticated detectors, they kept finding new particles. Lots of them. Particles with strange properties. And I mean that literally. Some of these particles were produced quickly in collisions, which suggested they interacted via the strong force, but they decayed slowly, which suggested they didn't. This mismatch was so puzzling that physicists assigned a new quantum number to these particles and called it, with characteristic bluntness, strangeness. A particle with strangeness could be produced easily in pairs, one with positive strangeness, one with negative, but couldn't decay via the strong force because strangeness had to be conserved in strong interactions. It could only decay through the weak force, which was much slower. Abraham Pace proposed this idea of associated production in 1952, and Murray Gell-Mann and Kazuo Nishijima independently formalized the strangeness quantum number around 1953. By the mid-1950s, the situation was almost comical. There were so many new particles, pions, kaons, lambda particles, sigma particles, Z particles, and more, that Enrico Fermi reportedly said, "If I could remember the names of all these particles, I'd be a botanist." The elegant simplicity of protons, neutrons, and electrons was gone, replaced by what people started calling the particle zoo. Dozens of supposedly fundamental particles, with no obvious organizing principle, no periodic table to make sense of them all. It felt like the early days of chemistry before Mendeleev, when you had a long list of elements, but no framework to understand why they existed or how they related to each other. And that's exactly the kind of moment when physics tends to make its biggest leaps. When the data becomes overwhelming, when the zoo gets too crowded, someone eventually notices a pattern. Someone finds the hidden order underneath the chaos. In this case, that someone was Murray Gell-Mann, and independently, Yuval Ne'eman. And what they found would reshape our entire understanding of what matter is actually made of, pushing the frontier one level deeper, below protons and neutrons, into a realm of particles that no one has ever seen in isolation, particles that are permanently confined inside the things they build. But to understand what Gell-Mann did, you first need to appreciate just how desperate the situation had become by the early 1960s, and how a tool borrowed from pure mathematics, group theory of all things, turned out to be the key that unlocked the whole puzzle. Group theory is one of those branches of mathematics that sounds incredibly abstract, and honestly, it kind of is. It's the study of symmetry. Not just the everyday symmetry of a butterfly's wings or a snowflake, but a much deeper, more general notion of symmetry. The idea is that you have a set of transformations you can apply to something, and after each transformation, certain properties stay the same. That's a symmetry. And mathematicians had spent decades classifying all the different kinds of symmetry groups, giving them names, working out their internal structure. Most physicists in the 1950s didn't think much about group theory. It was a tool that had shown up in quantum mechanics here and there. The rotation group, for instance, was essential for understanding angular momentum and spin. But the idea that group theory could organize the particle zoo, that wasn't obvious at all. Gelman saw it, though, and so did Yuval Ne'eman, an Israeli military officer turned physicist who was working on his PhD in London under Abdus Salam. Independently, around 1961, both of them realized that the messy collection of hadrons, that's the collective name for particles that feel the strong force, so your protons, neutrons, pions, kaons, all those zoo animals, could be organized into neat geometric patterns if you used a particular symmetry group called SU3. Now, SU3 stands for the special unitary group of degree 3. Don't worry too much about the formal definition. What matters is what it does. SU3 has 8 generators, 8 independent symmetry operations. And when you use it to classify particles, they naturally fall into multiplets, specific groupings of particles that share certain properties. The most common patterns are octets, groups of 8, and decuplets, groups of 10. Here's where it gets beautiful. Gelman took the 8 lightest baryons, that's the heavier hadrons, the ones built from what we'd later understand as 3 quarks, and arranged them on a diagram based on 2 properties, their electric charge and their strangeness. The proton and neutron sat at the top. The sigma particles, sigma plus, sigma 0, sigma minus, sat in the middle row. The xi particles, sometimes called cascade particles, sat near the bottom, and the lambda particle sat right in the center. 8 particles, arranged in a hexagonal pattern with 2 in the middle, a perfect octet under SU3 symmetry. He did the same thing with the mesons, and they fell into octets too. Gelman, who had a flair for language and a deep love of literature, called this classification scheme the Eightfold Way, borrowing the name from Buddhism's Noble Eightfold Path. It was a poetic touch for what was really a mathematical triumph. Now, you might be thinking, okay, so you arranged some particles in a pretty pattern. So what? And that's a fair question. The real test of any organizational scheme isn't whether it can categorize what you already know. It's whether it can predict something you don't know yet. Mendeleev's periodic table wasn't just a chart. It predicted the existence and properties of undiscovered elements. And the Eightfold Way did exactly the same thing. In 1962, Gelman was at a conference at CERN, the big European particle physics lab in Geneva, and physicists were discussing a newly discovered set of particles that seemed to fit into a decuplet, a group of 10 under SU3. They had 9 of the 10 slots filled. There were 4 delta particles, 3 sigma star particles, and 2 xi star particles. But the 10th slot, the one at the very bottom of the triangular arrangement, the particle with strangeness -3 and a specific predicted mass, that slot was empty. No one had ever seen such a particle. Gelman stood up and predicted it. He said there must be a particle with these exact properties, electric charge of -1, strangeness of -3, and a mass of approximately 1,680 mega-electron volts. He even suggested a name for it, the omega-. Neyman made the same prediction independently. Think about the audacity of that for a moment. You're standing in front of the world's top physicists and saying, based on the mathematics of an abstract symmetry group, that a specific particle with specific properties must exist, even though no experiment has ever detected it. That's the kind of prediction that either makes your career or destroys your credibility. There's no middle ground. It took about 2 years. In early 1964, a team at Brookhaven National Laboratory on Long Island, led by Nicholas Samios, found it. They were using a bubble chamber, a descendant of the cloud chamber that Anderson had used to find the positron, but filled with liquid hydrogen instead of supersaturated vapor. A high-energy kaon beam slammed into the hydrogen, and in the resulting spray of particles and tracks, they found one event, just one, initially, that matched the omega- perfectly. The mass was right. The charge was right. The strangeness was right. The decay products were right. It was a needle in a haystack, a single photograph among tens of thousands, but it was unmistakable. And just like that, the Eightfold Way went from a clever classification scheme to a confirmed theory. The mathematical patterns weren't just bookkeeping. They reflected something real about the underlying structure of matter. SU3 symmetry wasn't an accident. It was telling us something profound. But what? Why did these particles fall into octets and decuplets? What was the deeper reason? Here's the thing about SU3. When mathematicians study this group, they find that all its representations, all those multiplets, the octets and decuplets and so on, can be built up from a single fundamental representation, and that fundamental representation is a triplet, a group of 3. Which means that if you take the mathematics seriously, all those dozens of hadrons, all those zoo animals, could in principle be constructed from just 3 fundamental building blocks, combined in different ways. 3 ingredients, mixed and matched, producing the entire zoo. Gell-Mann saw this. So did George Zweig, a young physicist working independently at CERN. In 1964, the same year the omega- was discovered, both of them proposed that hadrons were not truly fundamental particles. They were composites, built from smaller, more basic entities. Gell-Mann called them quarks, a word he borrowed from a line in James Joyce's novel Finnegan's Wake. 3 quarks for muster mark. Zweig called them aces. History went with Gell-Mann's name. The original quark model proposed 3 types, or flavors, of quarks. Gell-Mann called them up, down, and strange. The up quark carried an electric charge of +2/3. The down quark carried a charge of -1/3. The strange quark also carried a charge of -1/3, but it had that additional property, strangeness, that the down quark lacked. And here's how you build the familiar particles from these ingredients. A proton, 2 up quarks and 1 down quark. Add up the charges. 2/3 plus 2/3 minus 1/3 equals +1. That's the proton's charge. A neutron, 1 up quark and 2 down quarks. 2/3 minus 1/3 minus 1/3 equals 0. Neutral, just like it should be. The lambda particle, the strange one. An up quark, a down quark, and a strange quark. The strange quark brings the strangeness. The omega-, that triumphant prediction. 3 strange quarks, strangeness of -3, charge of -1. Everything fits. Mesons, meanwhile, aren't made of 3 quarks. They're made of a quark and an antiquark, a quark paired with its antimatter counterpart. A positive pion is an up quark paired with an anti-down quark. A kaon involves a strange quark or anti-strange quark paired with an up or down partner. Every hadron in the zoo, every single one, could be explained as either three quarks bound together, that's a baryon, or a quark-antiquark pair, that's a meson. The entire zoo reduced to combinations of three fundamental objects. Now this was elegant, but it was also deeply weird. Those fractional electric charges, 2/3 and -1/3, nobody had ever seen a fractional charge in nature. Electric charge had always come in whole units. The electron has charge -1. The proton has charge +1. Every charge ever measured was a whole number multiple of the electron's charge. And here was Gell-Mann proposing particles with 1/3 and 2/3 of that fundamental unit. Many physicists were skeptical. Some thought quarks were just a mathematical trick, a bookkeeping device that happened to produce the right answers without being physically real. Gell-Mann himself was sometimes cagey about this, occasionally suggesting that quarks might be purely mathematical rather than concrete objects rattling around inside protons. But here's what's really fascinating about the quark model and what made it so hard to either confirm or dismiss. Nobody could find a free quark. People looked. They looked hard. Experimenters searched cosmic rays. They smashed particles together at higher and higher energies. They even checked the charge of tiny oil droplets in updated versions of Millikan's old experiment, looking for anything with a fractional charge. Nothing. Not a single isolated quark, ever. And this wasn't a matter of not looking hard enough. It seemed to be a fundamental feature of how quarks behave. They are permanently confined inside hadrons. You cannot pry one out and hold it up for inspection. It's as if the quarks are connected by elastic bands that get stronger. The farther apart you try to pull them, eventually you put in so much energy that instead of freeing a quark, you create new quark-antiquark pairs from the energy itself, and those immediately bind into new hadrons. You never get a naked quark. Ever. This property is called confinement, and in the 1960s, it was deeply puzzling. How can you claim that protons are made of quarks if you can never see a quark by itself? It's a fair objection, and it haunted the quark model for years. The resolution would come from a series of experiments in the late 1960s and early 1970s that were, in spirit, remarkably similar to something we talked about much earlier, Rutherford's gold foil experiment. Remember that? Rutherford fired alpha particles at gold atoms and discovered, from the way they scattered, that the atom had a tiny, dense nucleus. Well, starting in 1967, physicists at the Stanford Linear Accelerator Center, SLAC, out in California, did essentially the same thing, but at a much smaller scale. They fired high-energy electrons at protons and watched how the electrons bounced off. And what they found was extraordinary. The electrons were bouncing off at sharp, wide angles, far more often than anyone expected. If the proton were just a smooth, uniform blob of matter, the electrons should have passed through with only gentle deflections, like rolling a marble through fog. But that's not what happened. The scattering patterns showed hard, sudden ricochets, and that could only mean one thing. The electrons were hitting something small and dense inside the proton. Point-like objects. Little nuggets of concentrated charge and mass sitting there inside what everyone had thought was a fundamental particle. The experiments were led by Jerome Friedman, Henry Kendall, and Richard Taylor, and the results they got between 1967 and 1973 were stunning. They called the hard objects inside the proton partons at first. Richard Feynman coined that term, actually, because he wanted a neutral word that didn't commit to any particular theory. He just wanted to say, look, there are parts inside the proton. Let's call them partons and figure out what they are. And it didn't take long to figure out that these partons had exactly the properties that Gell-Mann's quarks were supposed to have. They had fractional electric charges. They came in the right combinations. They had spin 1/2. Everything matched. Think about what that meant. For years, quarks had been this awkward theoretical idea, useful for classification, sure, but maybe just a mathematical trick, maybe not real particles at all. And now here were Friedman, Kendall, and Taylor, essentially photographing the quarks inside the proton. Not directly, of course. You can't take a picture of something that small. But the scattering patterns were like shadows on a wall. You could read the shape of what was inside by studying how the electrons bounced. It was Rutherford all over again, just 60 years later, and at a scale 100,000 times smaller. The three of them would share the Nobel Prize in 1990 for this work, and it's one of those Nobel Prizes that was absolutely inevitable. They proved quarks were real, physical objects. But here's the thing. The deep inelastic scattering experiments didn't just confirm quarks. They also revealed something unexpected. When physicists carefully analyzed all the momentum carried by the quarks inside a proton, they found that the quarks only accounted for about half of the proton's total momentum. Half. So where was the rest? Something else was in there, carrying momentum but not interacting with the electrons in the same way. And that something turned out to be the particles responsible for holding the quarks together, the carriers of the strong force. They're called gluons. And now we need to talk about the strong force properly, because this is where the story gets really beautiful and really strange. Remember Yukawa's idea from 1935 that the strong force between protons and neutrons was carried by mesons? That was a good idea, and it was partly right. Mesons do mediate a residual strong force between hadrons. But once you know that protons and neutrons are made of quarks, you realize there must be a deeper force operating at the quark level, holding the quarks together inside each hadron. That deeper force is the real strong force, and the theory that describes it is called quantum chromodynamics, QCD. It was developed through the late 1960s and into the 1970s, and it's one of the great intellectual achievements of 20th century physics. Here's how it works, roughly. Each quark carries something called color charge. Not actual color, obviously. This is just a label, a name for a property that has no everyday analogy. There are 3 types of color charge: red, green, and blue. And the gluons are the particles that carry the strong force between quarks, just like photons carry the electromagnetic force between electrically charged particles. But here's what makes QCD so different from electromagnetism and so much wilder. Photons are electrically neutral. They carry the electromagnetic force, but they don't themselves have electric charge. Gluons, on the other hand, carry color charge. They're not neutral. A gluon carries one color and one anticolor simultaneously, and that means gluons interact with each other. They feel the very force they transmit. Let that sink in for a second. It's as if the postal workers delivering your mail were themselves made of mail. The force carriers interact with each other. And this self-interaction is what makes the strong force so fundamentally different from electromagnetism. It's what causes confinement. It's why you can never isolate a quark. The gluon field between 2 quarks doesn't spread out and weaken with distance the way an electric field does. Instead, it forms a narrow tube. Sometimes people call it a flux tube or a string. and the energy in that tube stays roughly constant per unit length. So as you try to pull two quarks apart, the energy in the tube grows and grows, linearly, until there's enough energy to pop a new quark-antiquark pair out of the vacuum. The tube snaps, and instead of getting a free quark, you get two new hadrons. It's like trying to isolate one end of a magnet by cutting it in half. You just get two smaller magnets, each with a north and south pole. You never get a monopole. The people who figured out the key mathematical properties of QCD were David Gross, Frank Wilczek, and David Politzer, and they did it in 1973. What they discovered is called asymptotic freedom, and it's genuinely one of the most surprising results in all of physics. They showed that the strong force gets weaker at very short distances, or equivalently, at very high energies. The closer two quarks are to each other, the less they feel the strong force. When quarks are right on top of each other inside a proton, they're almost free. They barely interact. But as they move apart, the force grows stronger and stronger, pulling them back. It's the exact opposite of every other force we're used to. Gravity gets weaker as you move apart. Electromagnetism gets weaker as you move apart. The strong force gets stronger. And this asymptotic freedom is precisely why the deep inelastic scattering experiments at SLAC worked. The high-energy electrons were probing such tiny distances that the quarks inside the proton were behaving almost as free particles. At that scale, the strong force was weak enough that you could ignore it and treat the quarks as independent little scattering centers. Gross, Wilczek, and Politzer won the Nobel Prize in 2004 for this discovery. So by the mid-1970s, the picture was coming together. You had quarks, up, down, and strange, held together by gluons inside hadrons. You had a rigorous mathematical theory, QCD, that described the strong force. And you had experimental confirmation from SLAC. But the story wasn't complete yet, because there weren't just 3 quarks. There were more to come. The 4th quark, the charm quark, had actually been predicted before it was discovered. Sheldon Glashow, John Iliopoulos, and Luciano Maiani had argued in 1970 that a 4th quark was needed to fix some technical problems in the theory of weak interactions. Without it, certain particle decays should have happened that were never observed. Adding a 4th quark with specific properties canceled out those unwanted processes beautifully. It was an elegant theoretical argument, but like the quark idea itself, it needed experimental proof. That proof came in November 1974 in one of the most dramatic episodes in particle physics history. 2 teams, working completely independently, discovered the same particle at almost exactly the same time. Samuel Ting's group at Brookhaven National Laboratory on Long Island found it by smashing protons into a beryllium target and carefully sifting through the debris. Burton Richter's group at SLAC found it by colliding electrons and positrons head-on and looking for resonances, sharp spikes in the production rate at specific energies. Both teams found a particle with a mass of about 3.1 billion electron volts, roughly 3 times the mass of a proton, and it was astonishingly narrow. In particle physics, narrow means the particle lives a long time before decaying, and this one lived about 1,000 times longer than you'd expect for a particle that heavy. That was the clue. That abnormally long lifetime was a signature that something new was going on. Ting called it the J particle. Richter called it the PSI particle. Neither wanted to give up their name, so the physics community, in a charmingly diplomatic compromise, calls it the J/PSI to this day. And what was it? It was a bound state of a charm quark and a charm antiquark. A new kind of meson, made entirely from this fourth flavor of quark that Glashow, Iliopoulos, and Maiani had predicted. The discovery was so electrifying that people called it the November Revolution. Ting and Richter shared the Nobel Prize in 1976, just 2 years later, which tells you how important the physics community considered this finding. The charm quark's discovery blew the doors open. If there were 4 quarks, could there be more? And indeed, in 1977, Leon Lederman's team at Fermilab near Chicago discovered the upsilon particle, a bound state of a 5th quark called the bottom quark and its antiquark. The bottom quark was much heavier than charm, about 4.2 billion electron volts, and its discovery immediately raised a question. Quarks seem to come in pairs, up and down, charm and strange, bottom and what? There should be a 6th quark. People called it top, and they went looking for it. But top was heavy, really heavy, much heavier than anyone initially expected. The search for the top quark became one of the longest hunts in particle physics, stretching from the late 1970s all the way to 1995. Every time a new accelerator came online, people hoped it would have enough energy to produce top quarks, and every time, for nearly 2 decades, the answer was no. The top quark was always just beyond reach. When it was finally discovered at Fermilab in 1995 by 2 competing detector teams called CDF and D0, its mass turned out to be about 173 billion electron volts. That's roughly the mass of an entire gold atom, all packed into a single quark. It's absurdly heavy for a supposedly fundamental particle, and to this day, nobody really understands why the top quark is so much more massive than all the others. So by 1995, all 6 quarks had been found. Up, down, charm, strange, top, bottom. 3 pairs arranged in 3 generations, and a remarkably similar pattern was playing out on the other side of the particle zoo, with the leptons. Because quarks aren't the only fundamental matter particles. There are also the leptons, and they've been with us almost from the very beginning of this story. Remember J.J. Thomson, back in 1897, firing cathode rays through his glass tubes and watching them bend in electric and magnetic fields. That little particle he found, the electron, that was the first lepton anyone ever discovered. And for a long time, it was the only one people knew about. But just like quarks, the lepton family turned out to be much bigger and stranger than anyone expected. Let's start with what makes a lepton a lepton. The word itself comes from the Greek leptos, meaning thin or small, which made sense at the time because the electron was by far the lightest particle anyone knew about. But the name turned out to be a bit misleading because some leptons are actually quite heavy. What really defines a lepton is simpler than that. Leptons are fundamental particles that don't feel the strong nuclear force. That's the key distinction. Quarks feel all 4 fundamental forces: gravity, electromagnetism, the weak force, and the strong force. Leptons feel everything except the strong force. They just don't participate in it. They don't carry color charge, so gluons have nothing to grab onto. A lepton can pass right through a proton's interior, in a sense, without getting tangled up in all that strong force business. It's like being at a party where everyone is shouting in a language you don't speak. The conversation just doesn't involve you. So the electron was the first lepton, discovered in 1897. And for decades it seemed like the only one. But then, in the 1930s, Wolfgang Pauli, that brilliant, acerbic Austrian physicist we've encountered before, noticed something troubling about a type of radioactive decay called beta decay. When a neutron decays into a proton and emits an electron, the energy books didn't balance. The electron came out with varying amounts of energy, sometimes a lot, sometimes a little, and the total energy before and after the decay didn't add up. Energy seemed to be disappearing. Now, some physicists, including Niels Bohr, were willing to consider that maybe energy conservation just didn't hold at the subatomic level. But Pauli wasn't having it. In December 1930, he wrote a famous letter to a physics conference in Tübingen. He couldn't attend because he was at a ball in Zurich, which is such a Pauli detail. And in this letter, he proposed that there must be another particle being emitted alongside the electron, one that was carrying away the missing energy. He called it the neutron at first. But when Chadwick discovered the actual neutron in 1932, the Italian physicist Enrico Fermi gave Pauli's particle a different name, the neutrino, Italian for little neutral one. And here's the thing about neutrinos. They're almost impossibly difficult to detect. They have no electric charge, so they don't interact electromagnetically. They don't feel the strong force. The only forces they respond to are gravity, which is absurdly weak at the particle level, and the weak nuclear force, which has an extremely short range. This means a neutrino can pass through essentially anything. Right now, as you're lying there, billions of neutrinos from the sun are passing through your body every second. They're passing through the entire Earth without hitting anything. A neutrino could travel through a wall of lead a light-year thick and have a reasonable chance of making it through without interacting with a single atom. They're ghosts. Pauli himself was so troubled by proposing a particle that seemed almost impossible to find that he reportedly said, "I have done a terrible thing. I have postulated a particle that cannot be detected." But he was wrong about that. In 1956, two American physicists named Clyde Cowan and Frederick Raines managed to detect neutrinos for the first time. They set up their experiment right next to a nuclear reactor at the Savannah River site in South Carolina, because reactors produce enormous numbers of neutrinos, or more precisely, antineutrinos, as byproducts of all that beta decay happening inside the fuel rods. Even with trillions of neutrinos flooding through their detector every second, they only caught a handful of interactions per hour. But it was enough. They sent a telegram to Pauli, who reportedly drank an entire bottle of champagne in celebration. Raines eventually received the Nobel Prize for this work in 1995, though sadly Cowan had passed away by then. So by the mid-1950s, the known leptons were the electron and the electron neutrino, because as it turned out, the neutrino associated with beta decay was specifically partnered with the electron. They came as a pair, just like quarks. And then things got weird, because remember the muon, that particle that kept showing up in cosmic ray experiments in the late 1930s, the one everyone initially confused with Yukawa's meson. The muon turned out to be nothing like a meson at all. It was a lepton. It was basically a heavier copy of the electron, about 207 times heavier, with the same electric charge, the same spin, the same fundamental properties, just more massive. When the physicist I. Rabi heard about the muon, he famously quipped, "Who ordered that?" Because there was absolutely no theoretical reason for the muon to exist. Nobody had predicted it. Nobody needed it. It just showed up, like an uninvited guest who turns out to be a permanent resident. And in 1962, Leon Lederman, Melvin Schwartz, and Jack Steinberger performed a beautiful experiment at Brookhaven National Laboratory that showed the muon had its own neutrino. A muon neutrino, distinct from the electron neutrino. They created a beam of neutrinos from pion decays and showed that these neutrinos only produced muons when they interacted, never electrons. This proved there were two different flavors of neutrino, each paired with its corresponding charged lepton. They won the Nobel Prize for this in 1988. So now you can start to see the pattern forming. Electron and electron neutrino. That's the first generation. Muon and muon neutrino. That's the second generation. And if quarks come in 3 generations, shouldn't leptons as well? The answer is yes, and the third charged lepton was discovered in the mid-1970s by Martin Pearl at the Stanford Linear Accelerator Center, the same facility where those deep inelastic scattering experiments had revealed quarks. Pearl's team found evidence of a new heavy lepton starting in 1974, and after careful work to rule out other explanations, they confirmed the tau particle with a mass about 3,477 times that of the electron. It was enormous for a lepton, and naturally, it came with its own neutrino, the tau neutrino, which wasn't directly detected until the year 2000 by the donut experiment at Fermilab. So there you have it, 6 leptons arranged in 3 generations, perfectly mirroring the 6 quarks. Electron, muon, tau, each with its own neutrino. Up, down, charm, strange, top, bottom, 3 pairs of quarks. The symmetry is striking, and it's not a coincidence. It turns out that for the mathematics of the theory to be consistent, specifically for certain quantum mechanical anomalies to cancel out, the number of quark generations and lepton generations has to match. If they didn't, the theory would produce nonsensical, infinite predictions. Nature, it seems, insists on this balance. Now, all of these particles, the 6 quarks, the 6 leptons, these are the matter particles, the fermions. But we've also been talking about forces this whole time, and forces are carried by a completely different category of particles called bosons. The photon carries the electromagnetic force. The gluons, all 8 of them, carry the strong force. And the weak force, the one responsible for beta decay, the one that neutrinos feel, is carried by 3 massive particles called the W+, the W-, and the Z0 bosons. These were predicted theoretically in the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, who showed that electromagnetism and the weak force are actually 2 aspects of a single unified force, the electroweak force. At very high energies, they behave as one force. At the lower energies of everyday life, they look different because the W and Z bosons are very heavy, about 80 and 91 billion electron volts respectively, while the photon is massless. Glashow, Salam, and Weinberg won the Nobel Prize in 1979 for this unification, and the W and Z bosons were experimentally discovered in 1983 at CERN by Carlo Rubbia and Simon van der Meer's team, earning them the Nobel Prize in 1984. And this brings us to perhaps the most famous particle of all, the one that took the longest to find and generated the most headlines when it finally showed up: the Higgs boson. Here's the problem it solves. In the basic framework of quantum field theory, all the fundamental particles should be massless. The mathematics works beautifully for massless particles, but obviously, most particles do have mass. The W and Z bosons are very heavy, quarks have mass, charged leptons have mass. So, where does mass come from? In 1964, several groups of physicists independently proposed a mechanism. Peter Higgs in Edinburgh, Francois Englert and Robert Brout in Brussels, and Gerald Guralnick, Carl Hagen, and Tom Kibble in London, all published papers within weeks of each other describing what we now call the Higgs mechanism. The idea is that there's a field, the Higgs field, that permeates all of space. Different particles interact with this field to different degrees, And that interaction is what gives them mass. Think of it like walking through a crowded room. A celebrity walks in, and everyone clusters around them, slowing them down. That's like a heavy particle interacting strongly with the Higgs field. An unknown person walks through, and nobody notices. That's like a light particle, barely interacting with the field. And a photon? A photon is like someone who somehow passes through the crowd without touching anyone at all. Completely massless, because it doesn't interact with the Higgs field. The Higgs field itself should have a corresponding particle, a ripple in the field, essentially. And that's the Higgs boson. But finding it required enormous energies, and for decades, no accelerator was powerful enough. The search became one of the driving motivations for building the Large Hadron Collider at CERN, a 27-kilometer ring of superconducting magnets buried beneath the French-Swiss border near Geneva. The LHC smashes protons together at nearly the speed of light, reaching energies of 13 trillion electron volts, and on July 4, 2012, two independent detector teams, ATLAS and CMS, each involving thousands of physicists from dozens of countries, announced that they had found a new particle consistent with the Higgs boson, with a mass of about 125 billion electron volts. Peter Higgs and François Englert received the Nobel Prize in 2013. Brout had passed away in 2011, just a year before the discovery. So that's the standard model of particle physics. 12 matter particles, 6 quarks and 6 leptons, arranged in 3 generations, 4 force-carrying bosons, the photon, the gluons, the W and Z bosons, and the Higgs boson, which gives mass to the particles that have it. It's one of the most successful scientific theories ever constructed. Its predictions have been confirmed to extraordinary precision. The magnetic moment of the electron, for instance, has been calculated and measured to agree to better than 1 part in a trillion. That's like predicting the distance from New York to Los Angeles and being accurate to the width of a human hair. And yet, the standard model is not complete. It doesn't include gravity. It doesn't explain dark matter, which makes up about 27% of the universe's energy content, but doesn't correspond to any known particle. It doesn't explain dark energy, which is driving the accelerating expansion of the universe. It doesn't explain why there's more matter than antimatter in the universe, why we exist at all instead of everything having annihilated in the first moments after the Big Bang. It doesn't explain why neutrinos have mass, because in the original standard model, they were supposed to be massless. But experiments in the late 1990s and early 2000s showed that neutrinos oscillate between flavors as they travel, and that oscillation is only possible if they have tiny but non-zero masses. It doesn't explain why there are exactly 3 generations of matter, or why the particles have the specific masses they do. The top quark is about 75,000 times heavier than the up quark, and nobody knows why. So the standard model is like a magnificent building that you know is part of something larger. The architecture is breathtaking, the engineering is precise, but you can see doorways that lead to rooms that haven't been built yet. Physicists are working on what might lie beyond: supersymmetry, string theory, extra dimensions, grand unified theories. But so far, no experiment has confirmed any of these ideas. The LHC has found the Higgs boson, but as of now, nothing beyond the standard model. The universe is keeping its deeper secrets close. But think about what we've traveled through tonight. We started with Democritus, sitting on a Greek hillside 2,400 years ago, imagining that if you cut matter small enough, you'd eventually reach something uncuttable. And through centuries of wrong turns and brilliant guesses and painstaking experiments, Dalton's ratios, Thomson's cathode rays, Rutherford's gold foil, Planck's desperate hypothesis, Einstein's stubborn light quanta, Bohr's orbits, de Broglie's audacious waves, Heisenberg's matrices, Schrödinger's equation, Dirac's beautiful spinor, Anderson's cloud chamber photograph, the bewildering particle zoo, Gell-Mann's eightfold patterns, the quarks that nobody believed in until SLAC's electron beam tore protons apart. Through all of that, we arrived at something genuinely remarkable. A theory that accounts for almost everything we can see and measure in the physical universe, built by thousands of human beings across generations, each one adding a piece, correcting a mistake, asking the next question. And the questions haven't stopped. They never do. That's maybe the most comforting thing about physics. It's never finished. There's always another layer, another mystery, another late night in a lab or at a blackboard where someone stares at an equation and thinks, what if? What if this is wrong? What if there's something deeper? The universe has been extraordinarily generous with its puzzles and extraordinarily patient with our slow, stumbling attempts to solve them. So let that settle over you now. All those particles, all those forces, all those names and dates and discoveries, let them drift. You don't need to hold on to any of it. The quarks and leptons and bosons will still be there in the morning, doing exactly what they've always done, holding the world together in ways that took us centuries to even begin to understand. And that's a pretty good thought to fall asleep to.